Good afternoon, everyone. Our speaker today is Filippo Maccagni, who graduated in 2013 in Bologna with Cimatti, Vignali, and Fraternali, then moved to Astron in the Netherlands when he got, in 2017, his PhD, working under the supervision of Professors Morganti and Osterlo. He then spent the latest 4 years in Cagliari working in Paolo Serra's group, and in particular on MeerKAT observations of Fornax A, which is also the subject of today's talk. And he just, since very recently, since October, he moved back again to Astron, held in a postdoc position, working again on a large survey program with MeerKAT, and in particular, working on H1 observations of nearby galaxies. Please, Filippo, the stage is yours.
Thank you, everybody, and good afternoon. So today I'm gonna present the work that I did in the last 4 years while I was a postdoc in Cagliari, and most of this work had received the help of the people in Cagliari that are led by Paolo Serra. We should also mention certainly Dane Kleiner, and Matteo Murgia, and Federica Govoni, Daniel Molnar, and Francesca Loi. And therefore, also you will see the names further. And I would also like to mention, since this is a talk given in Bologna, even though virtually, that the results on feeding and feedback in Fornax A also received a lot of support and help by Max Gaspari. Now, today here we're going to talk about this nearby radio galaxy that you see in the background. And how do I cannot, okay. And the Fornax A is located in the Fornax cluster, actually at the edge of it, in the bottom right corner, compared to the Fornax cluster that you see here in the optical image. Now, thanks to the MeerKAT Fornax survey, we could observe in the radio and the H1 at 1.4 GHz, the environment of Fornax A, which is this elliptical galaxy in the center. And here in the blue contours, you see all the H1 clouds and streams that we found associated to this galaxy, and of course, also to other galaxies of the group. Now, I refer you to the papers of Paolo and Dane to understand the history of this H1 that was likely brought in by a gas-rich merger that occurred 1 giga-year ago. Of course, we do not only have the H1 information, but we also have the radio continuum, and here you see overlaid part of the H1 contours in red with the radio continuum emission. And these lobes extend for around 300 kiloparsecs in diameter. What I did is to study the spectral energy distribution in the radio wavelength of Fornax A to understand the history of his AGN. So in the first part of this talk, I'm going to talk about these radio continuum observations where we combined information from 84 megahertz to 217 gigahertz in the Planck frequencies to understand the history and time scale of Fornax A. And in the second part, I'm going to talk about a more recent paper that was just published there, where we combine the information on the gas, so the H1, but also the molecular gas and the ionized gas seen by ALMA and MUSE to understand what is going on in the innermost 6 kiloparsec and what is likely feeding this AGN. Now, you may very well know that from the shape of the spectral energy distribution, we can understand the age of the radioactivity. So, for example, here you see the flux density changing as the time passes. And first you saw an active phase of the AGN, and then you see a dying phase. So the AGN is not injecting high energy particles into the medium. And once has an information on the shape of this flux density given by multi-wavelength observations in the radio wavelengths, it's possible to measure the distance between these two frequency breaks. And these two frequency breaks give us are directly related to the age of the radio source. So what we did with Fornax is to combine the information given by MeerKAT. Here you see only the radio emission, with also, for example, the SRT at 5 GHz, and at lower frequencies, the MWA, and higher frequencies, Planck. And we separated this study into different components. So the first components are the lobes, for which you see in the top, in the right, the western lobe, and in the left, the eastern lobe, and they show a similar shape in the distribution. And also, compared to the lobe, what is very interesting is that these lobes are very spherical and quite extended. So if one takes the radiative age given by the flux density here in red, gets an age of around 24 megayears, while if one takes the dynamical expansion of these lobes, they infers an age of around 200 megayears. So what we actually infer is that multiple episodes of what we think it happened is that multiple episodes of AGN activity must have injected particles in the lobes, the last phase of which started approximately 24 megayears ago and ended around 12 megayears ago. So it's a quick, the last phase that we saw, it's a quick phase, but probably there were multiple phases previous to this that injected the lobes. And this is given by the fact that these lobes are quite spherical, while they're typically oblate if they were more recently injected, for example. Now we also focused on the central component, which we call the central jets that you see here as a shape at 1.4 gigahertz, and then we use also some resolution, but we went also with ALMA frequencies at 100 gigahertz. Now we did the same study of the flux density, and we separated the jets components into one is the kiloparsec core, and the other is the outer jets. So here we see again that the two distributions are quite different, and we could infer that likely what happened is that the jets are tracing a phase that is now switched off, but very recently, only 1 megayear ago, and this phase is not connected to the formation of the lobes, since also we do not see any physical or any emission that actually connects this central 6 kiloparsecs lobes to the with the outer 6 kiloparsecs exact with the outer lobes, but likely, as is also seen in many nearby radio AGNs, the core is right now active. So what we are seeing is that Fornax A is flickering in its AGN activity, which means that we have a very fast switch off, a switch on between of the AGN. And for the central regions, we see two phases in the last 3 megayears. Now we also saw from the H1 observations a lot of material that was brought in, but the event that brought in this material into the group is likely not connected to the latest phases of activity that we see in Fornax A. So what we did is to look better at the information given from the gas in the center. And in particular, we took the H1 observations, but also ALMA CO120 observations and MUSE observations, which consist in a mosaic, which is kind of a snapshot, so not high sensitivity, and then of a single pointing in the innermost arc minute. Now here you see the innermost 6 kiloparsecs of Fornax A with this dust lane. Not only lane in the center, but also kind of a shell. And this shell is also seen in the H1 here in yellow and in the CO. Now the resolution of the H1 and the CO is around 20 seconds, and it's not ideal to study in detail the kinematics of this the gas distribution. But you see that overall, there is a rotation along the northeast and southwest, southeast axis, but there is also gas with high dispersion perpendicular, for example, in this case, to the radio jets. To get better insights on the kinematics, we also rely on the information on the ionized gas, for which we have MUSE data that give us a high resolution information, in which where we really trace the different features in the innermost dark minute. Now, we also made a characterization with a multi-Gaussian component that revealed that really in the very center, as you see here in the central panels, but also along orthogonal stripes, a second broad component is needed to fully characterize the emission lines. And this broad component, you see it here in the moment 2 maps, how it is distributed. And not only the moment 2 maps shows that you have high dispersion, high velocity dispersion gas in the wake of the radio jets. To understand what is to really understand the kinematics of this gas, we look better at the combine the channel maps of the ionized glass here in blue, and the H1 in orange, and in green, the CO. Now you see here that the overall rotation, if you move from left to right, and then again from left to right, is given by the major axis of overall rotation is in the northwest southeast axis, where you see this gas that first is moving and then it moves on the other side here and finishes here around channel 2000 of kilometers per second in velocity. But also you see very broad gas in the center, that is for which you see extending from around 900 kilometers per second. And more in particular, you see this east-west stripe that is not compatible with any rotation of, with any model of rotation. So to better investigate the kinematics and to understand what is, so there is some gas that is rotating, but there must be some gas that is, it appears that there is some gas that is also not rotating. So what is this non-rotating gas doing? Now, for example, if we look at the line width of the ionized, but also of the H1 and of the CO, we see that there is a gas with line width at 80% of the total flux of 600 kilometers per second. And the distribution kind of follows the radio jets that you see here in the black contours and at the edge of the radio jets. Most importantly, if we take the extension here of the H1, which coincides with the shell of dust and also with some ionized gas that is seen in the shallow MUSE data, and we take the outflow velocity that we infer from the line width, we see that this gas should have reached these distances in around 3 megayears, which is exactly the total age of the radio jets. So we have a temporal coincidence between the velocities inferred from the gas and the jets, which suggests that maybe the 2 episodes, so this gas that may be outflowing, is related with the expansion of the radio jets. Now, something that is certainly not compatible with rotation, and which the kinematics do not suggest is gas outflowing, is this east-western stripe. And what we did is to draw the kinematical plot, which was first suggested by Max Gasperi in his paper in 2018, where you can see you basically take the gas and you measure it's a centroid, so it's a shift from its centroid, it's a shift with the systemic velocity, and then you measure the line dispersion. Now in green, you see all points that you see in the field of view of MUSE, and in blue, you see the pixels that we found are compatible with rotation, so mainly distributed along this the rotation axis, the major axis. Now you see that we find that there are a lot of points that have low velocity dispersion, and they spread throughout all values of shifts compared to systemic velocity. And we can trace from the kinematical plot where these points are found in the field of view. So here we see that in blue, in the field of view, is the distribution of the points compatible with rotation. And in green, you see the points that are located in the kinematical plot below the rotation, below dispersion velocities. And again, also in red, the ones that have high dispersions are found in the wake of the radio jets and at the edges. So this kinematical plot has an interesting power that in one snapshot, or two snapshots, it gives us an immediate reference between where in the distribution of the gas certain kinematical properties are located. And more interestingly, since it's we can also overlay the expectations of the kinematical conditions of this gas that are predicted by called chaotic accretion, which was why the first reason why this plot was suggested. So in this case here, in the purple ellipses, we plot the 1 sigma and 2 sigma contours of confidence contours for which a gas that if it was in falling because of cold chaotic accretion, we would expect to have these kinematical properties. And this gas in green is the gas that you were seeing here along the east-west filament that reaches the center of the galaxy. Now, taking also not only the kinematical properties, but also some other physical. Sorry? Yes, I have 2 slides.
No, sorry, someone spoke with the microphone on, but it wasn't.
Okay.
You still have a bit less than 10 minutes if you want.
Okay, so now, yes, I can. So we can also study in the cooling time versus the turnover time that gives us an idea on which, if the cooling time is dominating or not over the turbulence, and how if the turbulence is causing, for example, cooling. So if we are located in this region, in the chaotic accretion, in this region in purple, we have turbulence that is causing the condensation of the gas. And again, what we did is to take the gas that was rotating here in blue, the gas that was that showed kinematical properties similar to to an outflow, and the gas that showed the kinematical properties similar to gas that may be in falling, and the gas that may be in falling again is suggested that its infall may be caused by the turbulence, and the mechanism of this infall may be called chaotic accretion. So the interesting thing about this work is that we started from MeerKAT observations, which were actually from the commissioning of the instrument, and combining the continuum MeerKAT observations with other continuum observations from MWA, the Sardinia Radio Telescope, and Planck, we could understand that the duty cycle, so the on and off activity of Fornax A, is very quick, and this AGN is flickering with scales of a few mega years. Then going to observe the gas, and in particular the kinematics of the gas, and combining the information of the H1 with the CO and the ionized gas, we saw that in the innermost regions of Fornax A, there are clouds, for example, that may be pushed out by the radio jets and by the expansion of the previous phase of the activity. But there is also an east-west stripe that shows kinematical and physical properties consistent with the predictions of cold chaotic accretions, which in our opinion is the feeding mechanism of this AGN. And one other thing of cold chaotic accretion is that it's a mechanism that can easily sustain a fast recursive activity, which we are seeing here also from the continuum observations. So thank you very much, and I will take questions.
Thanks, Filippo. Are there questions from the audience? Please raise your hands. Well, meanwhile, let me start by asking two things. So I didn't get if this flickering activity, it's also seen as a possible precession of the jet. So if you try to correlate the large scale structure of the lobes and the smallest structure you can observe, and you just showed for last, is there any indication that the jet is precessing somehow?
Yes, this has always been a possibility, seeing this symmetrical and S shape that the jet may be precessing, even though what the H1 the 1.4 observations show here that there is no link, physical link between the jets here in the center at 6 kiloparsec and the radial lobes. So the emission of the jets finishes. So the lobes are not connected anymore. They must.
But still, they look roughly located more or less along the same axis. So maybe it's an on and off kind of thing, but without any significant change of direction. Can it be?
Yeah. But I mean, if there was an off, so the jets, based on their brakes, we can measure an age of around 12 mega years. So the lobes, while the jets appear much younger. So they appear to have been reinflated, but this younger phase did not reach the lobes, or it did not reach them to inject them significantly. That could also be a possibility. But yes, we didn't investigate in detail the precession, but we think it's not a real. And in this story, it's not very important.
Francesca, please.
Hi, Filippo. So concerning this stripe that you see and that you interpret as a possible accretion, I was wondering, do you detect any stellar component as well associated with this accretion, or do you think it's just accretion of gas?
Well, we didn't investigate in detail the stellar component. Here also we see that there is some dust along this stripe, for example, here. So we should investigate it also, for example, from the MUSE data, if there are differences compared to the other stars distributed in the field, but we didn't do it.
Okay, thank you.
Okay. Any more questions? I don't see any. Okay, so if there are no more questions, let me thank again our speaker. And I think it's the end for today. Thanks, Filippo. Yeah, hopefully we release the talk on YouTube.
Well, thank you very much. Thank you very much for the opportunity. And yeah, I hope you saw some nice images at least.
Yes, sure you did.
Okay.
Thanks. Bye, everyone.
Okay. Bye-bye.
Bye-bye.
Bye-bye, everyone.